Hey, welcome back. This is the second technical video in what will hopefully be a long series where we build up our own fully custom Linux distro that's specific for self-hosting. More importantly, this is the first video where we actually get to do something that's interesting for once. Let me show you an example of what we'll be doing today. So right now we've just got this main program. It's a hello world. We want to turn this into what we'll be using for our compositor. Normally, if you just install Linux, basic headless Linux, no desktop environment on it, you get just a text-based interface like what you can see here. If you look in the upper left here, you see it says TTY2. To my knowledge, every Linux distribution has multiple of these virtual terminals that you can switch between by holding down Control-Alt and then going through your F keys, F1, F2, F3. In this particular Linux that I've installed, F1 I have set up to be my main user interface, basically, my main compositor. And it's running what's called sway. So if we switch back to virtual terminal number 2, and if we log in, this is basically just, a prompt. We can do anything we can here in a normal terminal. You'll notice we don't have any sort of mouse. We can't do anything graphical, but we do have, text input and text output, obviously. So if we go to our Breezy application right now, if we were to run it, it's just a basic hello world. I told you earlier I was running sway, and if I run this command, which is a program installed on this computer, it loads a user interface, so I can launch terminal sessions. Multiple, I can move them around. These are all features of sway. So that's what we want to turn Breezy into. I can quit out of sway. There's a hotkey for it, and I can say yes, exit, and I get back to this terminal prompt. Then we can see that it was just a standard program that ran. So how do we go from this text-based prompt to a user interface? We have to set up our rendering stack inside of Breezy. But before we get into all of that fun coding, I've got some alphabet soup we got to decode. All right, so the main thing we're going to be working with today is called the DRM, which stands for Direct Rendering Manager. This is a Linux subsystem that's in charge of managing all the interactions with the GPU. So this is for things like if we want our application to render into a display buffer or scan that buffer out onto the screen, that would go through the DRM. There's a whole pipeline that we have to put in place to work with the DRM that involves a frame buffer, a plane, CRTC, encoder, and connector, but we'll talk about those later on in the video. Next up is GBM, which stands for Generic Buffer Management. This is a library that makes it a lot easier for us to allocate memory on our GPU. So primarily this is going to be for allocating our display buffer. After that, we'll be talking about OpenGL and EGL. OpenGL basically tells the GPU how to render images or text or any kind of graphic into our main GBM display buffer. So put simply, which colors to make which pixels. And then EGL is basically can be thought of as glue code. It manages a context for OpenGL to use, which, again, fancy way of saying it links OpenGL to our GBM buffer. All right, so what's on the docket for today? Well, first, we need to become the DRM master. Only one application at a time can hold that role, and whoever has that role is able to actually draw stuff out to the screen. So given that we're making a compositor that needs to draw things out to the screen, we need to claim that responsibility. Once that's in place, we can set up our DRM pipeline. This is setting up our different DRM resources like connectors and encoders, which actually allow us to send stuff out to the screen. As part of that, we're going to be allocating some memory through GBM, which is going to be for our main display buffer. We're going to create an EGL context that's linked to that GBM buffer, and then we're going to use OpenGL to actually draw stuff out onto that buffer. But for now, we're just going to draw out a solid color because that's easy and enough to prove that it's all working. And future videos will actually do stuff that's more interesting. All right, so before we get into the DRM stuff, I want to talk about two things. First, I added a logger to the project, and this is the header file for that. A very simple interface. We just call an initialize function, and then we call whichever log function we want to call based on the log level. So debug, info, warn, or error. If we check out main, we can see the first two lines of our main method. We initialize the logger to be logging for errors, then we set the level for DRM to be debug. The second thing I want to talk about are what are called seats, S-E-A-T. You can think of it as like a group of hardware for a specific seat at a computer. So it's like a mouse, keyboard, and monitor, for instance. And there's a program running on, as far as I know, basically every Linux install that helps manage these seats. For my particular Linux distribution, what I have installed is called seatd. If I jump to a terminal, we can see it running right here. The reason this matters is because one of our requirements for claiming DRM master is that we have to give it up when we switch between virtual terminals, and then reclaim it if we ever switch back to our compositor. So seatd, the seat daemon, takes care of all that for us, as long as we basically ask it to. For us to interact with seatd through our code, we needed to install a library called libseat. There's two options here, and pretty much any package manager you're using is going to show two options. One is the runtime library. This is what our compositor would need on like a normal running system, but since we're actually writing C code on this computer, which needs those header files and needs, that C code, we need the development package as well. All right, so jumping back to the code now. I created a DRM file to kind of hold all of this DRM related stuff that we need. And this is the external API for it. So first there's this bzdrm initialize function, which basically just bootstraps our DRM code, makes the proper claims that it needs, gets everything set up and listening to how it should be. And then there's a cleanup function, which basically does the opposite of all that. It releases all of those resources that we have claims on. And then there's this loop iteration. And this we're calling from inside of our event loop. This right now is just our very temporary event loop. Basically all this does is it checks some file descriptors that we're watching to see if any events got published. So if the user were to switch a virtual terminal, this is what would read and handle that change. All right, so if we take a quick look at the implementation for these, we don't have to go into too much detail here. But basically, libseat gives us this seat listener interface that we implement these two functions for, which handle the two events for either enabling or disabling a seat. So these will get fired whenever a user changes their virtual terminal. In our initialize function, we first open the seat. We do some prep work, doesn't really matter too much. And then we open the device that we want. And this is our graphics card. So by doing this, we're basically making that claim to be DRM master. We do a check to make sure that's the case, and then that's the end of our initialize function. Our loop iteration, we just specify which file descriptors we want to listen to. So we've got our seat and our DRM file descriptor. The DRM doesn't matter at this point. The seat one's the only one that matters. And basically, whenever something gets written to this seat file descriptor, we come through this if block, which dispatches a libseat event, which triggers either our enable or disable handlers. So if we take a look at this in action, let's jump over to our number 2 virtual terminal. We would do a meson compile, goes ahead and does its thing. And then to run this, I have it redirecting all output to this test output file, which just makes it a little easier to inspect. I'll go ahead and run this. It holds for about 3 seconds and then it exits. And if we take a look at our test output file, you can see it successfully did everything, but then it times out 3 times. So in our event loop, if we take a quick look at that, we only do 3 iterations of this iteration function. And this pulls those file descriptors waiting for 1 second. It's got a 1 second timeout. So if nothing gets written to this file descriptor after a second, then this function just returns and it comes out to this log statement here, which is what we were seeing. That's why it takes about 3 seconds to run. You would think that if we try to change virtual terminals during that 3-second period, that would cause an event to get written to this file descriptor, which would make this pull function return early. But if we actually test that out, it doesn't quite work that way. Oh, after quite a lot of troubleshooting, I found out that our program is actually what's preventing the hotkey from triggering. Since the hotkey is not firing, nothing is actually writing that event to the file descriptor, so no switch. So in order to test this, what I had to do was SSH into my computer from a different computer and manually run a command to change virtual terminals. Let me pull up my terminal for that. And then this is the command to change virtual terminal. I'm changing to virtual terminal number 1. So if I were to run this, what we can see, it changes my virtual terminal back to the main one. So let's do that again, only this time we're going to have our compositor running while we do it. So I'll get that run statement ready on both sides. I'll push one and then push the other. And you'll see, even though a program was running, it does switch over. All right, and if we were to take a look at our log file, we'll see that it does handle the seat event, and it does call that disable handler that we had and releases DRM master. So it does all work correctly. We just can't test it from this computer. But given that it works correctly, I think it's safe for us to move on. There's some more DRM setup we have to do. I still haven't quite finished all of it, but I figured I'd give you an update for what I have here. So still working inside this BZDRM file. I didn't change any of our public APIs for this yet. I did change how the main initialize function works. So if I take a quick look at that, basically I just split it into 2 pieces. So we've got the libseat stuff, which is what everything that used to be here before. And then I added this new BZDRM init, which initializes a few things for DRM. So in order for our compositor to write out to the monitor, we need to basically configure it. We need to tell it how to do that writing. So, you might have multiple monitors plugged in. One might be HDMI, one might be DisplayPort. There's a few other things we have to configure as well, but basically we've got to query these resources from the DRM subsystem and properly choose and configure each one independently. And that is basically what this DRM init function does. And I made a few helper functions down here as well. So if we jump over to it, so this takes the DRM file descriptor that we got from libseat earlier, and then we query all of our DRM mode resources. So the DRM mode resources basically gives us frame buffers, CRTCs, connectors, encoders, and a few other things. The frame buffer is literally just the pixel data that you want to display. These are the buffers that we're going to be creating with GBM. The CRTC, it stands for literally a CRT, like a cathode ray tube controller. So it's a bit of a outdated name, but it still applies for modern monitors. Basically takes that frame buffer, or frame buffers if we have multiple planes, and it shoves that data through an encoder, and the encoder would be something that encodes it into either like an HDMI or a DisplayPort signal. And that encoder is configured with a connector. The connector is like the physical port on your graphics card, so like an HDMI port, for instance. So this is what sends it out to the monitor. That's kind of the rough pipeline. The frame buffer goes through the CRTC into an encoder, which goes out through the connector. If we jump back to our init function, first we query all of our resources, grab the first connector that's valid, which basically means, hey, give me the first thing that's plugged into the monitor. You might have multiple monitors, so you might have multiple valid connectors, but we're just grabbing the first. There's this concept of a mode, which is basically your resolution and refresh rate, along with a few other things. So just for the sake of seeing something on the screen, I went ahead and printed those out. We're just going to be using the first mode because they're sorted based on what's optimal for that monitor. So we're just going to grab the first one off of it. Then we grab our CRTC for this connector with a valid encoder. And that's kind of as far as I made it. So there's a legacy way of doing what's called mode setting, which is basically applying all of these configurations. And then there's a more modern way called atomic mode setting. I'm trying to figure out how to get the atomic way working. You have to define a bunch of properties and apply all the properties at once. Supposedly it's a lot better, but it's also the one that I have no experience with, so that's what I'm currently scratching my head over. But what do we have so far? Let's take a quick look at the modes that we're printing out. All right, so if we go ahead and compile and then run our program, I'll just throw it into test output so it's easier for us to inspect. All right, so it goes through a lot of the same steps. We enable seat, claim DRM master, and then we start going through our different resources for DRM. So we have 4 connectors, which are 4 ports on the back of my graphics card. We're just going to grab connector number 1, because that's what my main monitor is plugged into. We then query the different modes for that monitor, which there are 17 of them. And I kind of printed the important stuff out below. So it's resolution followed by refresh rate. And you can see the top one here. This is basically the highest resolution with the highest refresh rate. So that's generally going to be the preferred. And we can see I'm also picking out an encoder with a CRTC. For the atomic mode setting, we'll need to have this atomic commit method, which basically every time that we render inside of our render loop, we're going to be calling into this. And the way atomic mode setting works is we would create a request, we would add a bunch of properties to our request, and then we would commit it. The tricky part that I've been working on is figuring out how to add these properties. So they take an ID for the property that you want to set, which is an integer, and then a value for that property. The tricky part is figuring out what these numeric IDs are for the different properties. So I created this utility function called getPropID, which takes the type of object you want to set, which is one of these things like CRTC, connector, encoder. They take the ID of the object, so this would be like the CRTC ID that we've saved, that we configured and saved earlier. And then they take a string name for that property that you want to look up. And then eventually it'll return that prop ID. It doesn't do that yet. Right now, all it's doing is getting a list of all of the properties that are set on that particular object of that particular object type, and then iterating over them and printing out the string name of each. So if we check that out, see what it looks like real quick. First we'll do a standard build. You can ignore the warnings because I've got a lot of test code in right now. So down here, kind of towards the bottom, we can see for CRTC objects, we have 13 properties, and then I list out the names here. So now that I know what the actual name values are, I'm able to take those names and look up their individual IDs so that then I can actually give them a value. All right, got the lookup working for our prop IDs. And I figured out a few of the properties that we're going to need to set inside of our atomic commits, at least for CRTCs and connectors. Looking into planes now. So the basic idea behind a plane is that a plane is associated with a buffer, and the planes essentially layer on top of each other. You might have like one primary plane, which is all of your, desktop background, windows, all of that stuff. And then you might have a second plane for just your mouse cursor. And the reason for that is it's much more efficient for your graphics card to display that. It only has to update these few pixels for the mouse cursor. It doesn't have to actually, touch or update that main overlay plane at all. All right, got the different properties figured out that we need for planes. They're basically here. So we need the frame buffer ID and CRTC ID. So this just basically ties this plane to this frame buffer and output. And then there's a bunch of configurations for the plane itself. So we've got a source XY width height and a CRTC XY width height. So the CRTC ones are for the output. So these are going to be basically our end destination on the screen. So our X and Y for this, main primary plane is just going to be 0, 0 because we want things drawn in the upper left of our monitor. And then the width height are just going to be our resolution. The source values are a bit different. They're in what is called 16.16 fixed point, which which is a new term I'd not heard of before, but basically it's a way to express floating point numbers as integers. So the 32-bit integer, you basically split down the middle. And the first 16 bits are the whole part of it, and then the last 16 bits are the fractional part of it. So then in our commit down below, where we set all of these things, the source values, we just need to shift left by 16 bits, and that's how we're going to get the integer part of them. So I mentioned they were 0, 0 for their xy, and then the width, height, these are going to be the resolution, which we're getting out of our mode that we chose. Still have one thing left to get working, and that's the frame buffer ID. But in order to have the frame buffer, I've got to have something that backs it, and that's where the GBM memory allocation comes into play. So that's what I'm working on now. Guys, so close to done. It won't work. So let's see, where did we leave off? Right, so I added GBM, and I started to define a few of the global variables we need for different things. If we jump down to where we're using these, so this is our DRM init method, the one that we've been, again, doing a lot of work in. This is where we create our GBM device. And then immediately after we create the surface, which I've just commented out because I'm trying to debug something that's driving me insane. Then down in our render loop, did a little more work down here. Where are we at? Here we go. So added a bunch of stuff down here. Basically doing some prep work for when we add OpenGL. This is where we'll render into the buffers. And we do the front and back buffer switch. And then we write out the buffer. On the first iteration, we need to initialize everything in our atomic commit. But then on subsequent calls, we just need to do, basically right now it's just the frame buffer ID. And that's because we're doing the double buffering where we swap which frame buffer is being displayed. Now, none of this is being called right now. If we check our main file, our main function. So we initialize our DRM system, and then we immediately call cleanup. So we don't actually do our placeholder event loop. This GBM device seems to be having a memory leak, which is making it so nothing is working. So we initialize it here. So we call create device. We make sure it's not null. And then down below, we say, hey, if it's not null, then call destroy. This, as far as I know, should be freeing everything. Those are the only uses of this GBM device. Yet if we come back here, compiles, fails to run, and gives us this memory leak. I have been hitting my head against the keyboard for way longer than I care to admit at this point, so. All right, good morning, everybody. It's a new day, at least for me anyways. I had a few ideas last night that I want to try this morning. First thing I want to give a shot is Valgrind. And to do that, I'm going to get rid of address sanitizer for now, and then we'll just rebuild our application and run it using the Valgrind command. There we go. Okay, so it's at least reporting the same 112 bytes lost, and this directly tells us, hey, GBM create device has the error. Interesting. So that at least confirms our theory. All right, well, one of the other ideas that I had was basically to just ignore my errors and move on. I am still intending to get it fixed, but my thoughts are maybe this create device method is creating an object that's not ready to be released yet. Maybe when we actually start using our GBM surfaces, that puts that object in a state where it's able to be released and then it gets properly freed. So I'm going to move on. I'm going to try to add EGL and OpenGL to the project and see if we still get these memory leaks here and see how that goes. All right, all of our OpenGL and EGL initialization is in place. EGL is what sets up the context, and OpenGL is what we actually render into. That's our graphics library. So EGL kind of works as the glue between OpenGL and all the DRM and GBM stuff we just set up. So we're actually using what's called OpenGL ES, and the ES is for embedded systems. So to get OpenGL ES, we are going to use something called GLAD, which is basically a website we go to download some header files and the C file. And what these do is they give us access to all of our OpenGL functions. OpenGL is a bit weird in that it needs to be dynamically loaded into your program. With that said, we defined a new OpenGL section inside of our DRM file. Got some global variables we'll need, and then a bunch of utility functions, have another init function which has most of the stuff that I've just added. We can jump down into it. It's still a work in progress, so we'll have to verify everything here works, but we go through, create a display, tell it that we're using OpenGL ES with EGL. This is where we create our GBM surface. So originally I had this up inside of our DRM init function right after we created the GBM device, but this is probably a better home for it. So I moved it down here. This surface is needed by EGL because EGL creates its own surface based on that one. And then we work with the EGL surface and it kind of does all the magic for us. Then we load our GLES API. So this is basically loading those files that we downloaded and stuck into our project. And that's pretty much it. There's a few other helper functions that I've defined down here, but I don't think I got to get into those. So at this point, I'm just going to try to integrate some of this EGL stuff into our render loop and then see if our memory leak from earlier went away. Guessing probably not, but who knows? I can hope, right? Got some good news, and I got some bad news. It builds. That's good news. So I'm going to run this quick, and behold your eyes on the beauty that is taking forever to run. And wait for it. Ta-da! Was that not the most colorful color that you've ever seen? Bad news is that we are leaking worse than a sieve. Yeah, so fun times. Okay, so I got some updates for our memory leaks. I went and consulted my good friend Claude, who basically told me this. So the short version is that it's kind of to be expected. Apparently GBM and EGL do some one-time initializations that they don't bother freeing because it adds overhead and doesn't give any benefit. So I created what are called suppression files, which summarize the current known leaks, and then both address sanitizer and Valgrind can take those suppression files in as parameters. And that basically makes it so that they don't, sit here and spew out those same problems again and again and again. All right, so I still have a little bit of code left to clean up. I'll probably take care of that this weekend and push the updates out to GitHub, I don't know, early next week. I just want to get this video posted because it's been a little while since the last video. Sorry about that. For the next video, I'll probably be looking into keyboard input, and that'll allow us to either switch between virtual terminals while our compositor is running, so we don't have to do that weird SSH trick again. But more importantly, it'll actually let us quit our compositor. So we can get rid of our really janky event loop and put something that's a little better in place that actually, waits indefinitely. And I'll probably do some, little fun, useless things with the keyboard as well, just to spice things up. But yeah, that's about it for this week. So catch you in the next one.